How does frequency response affect amplifier design? Imagine trying to listen to music or talk on a radio and noticing that some sounds are clear while others are muffled or distorted. That's where frequency response comes into play. It's a key factor in how amplifiers are built and how well they perform. Frequency response tells us how an amplifier handles different input signal frequencies. It shows which frequencies are amplified well and which are not. This is important because signals in real life come in a variety of frequencies. For example, audio signals range from 20 Hz to 20,000 Hz. Radio signals can go much higher. The main idea is that every amplifier has a range of frequencies it can handle effectively. This range is called the bandwidth. The lower cutoff frequency is where the amplifier starts to lose some of the signal, and the upper cutoff frequency is where it begins to drop off at high frequencies. The difference between these two is the bandwidth. For audio amplifiers, a typical bandwidth is from 20 Hz to 20,000 Hz. For radio frequency amplifiers, the bandwidth can be in the hundreds of megahertz or even gigahertz. Components like coupling capacitors and bypass capacitors influence the lower cutoff frequency. They block direct current and allow alternating current signals to pass, but their values determine how low the frequency can go. If these capacitors are too small, the amplifier might not handle low-frequency signals well. Parasitic capacitances and inductances inside transistors and wiring affect the high-frequency response. These tiny, unavoidable effects cause gain to drop at high frequencies and can create phase shifts. If not managed, they can lead to distortion or even cause the amplifier to oscillate. Designers also need to consider phase shifts. When the phase of the output signal shifts too much at high frequencies, it can make the amplifier unstable. This is especially important in feedback circuits, where stability is crucial. To balance all these factors, engineers often make trade-offs. Increasing bandwidth might reduce gain or increase distortion. They choose specific amplifier types and components to meet the needs of the application. Different uses have different requirements. For high-fidelity audio, flat gain across the audible range is essential. For communication systems, amplifiers might be designed to boost signals only in specific frequency bands. Understanding the frequency response helps engineers select the right components, layout, and topology to get the best performance. In practical terms, analyzing frequency response allows engineers to predict how an amplifier will behave with real signals. It ensures the output remains true to the input across the desired frequency range. This is vital for maintaining signal quality in analog electronics and embedded systems, where amplifiers are often the backbone of the circuit.